All right, today we're going to pull back the curtain on a concept that's really shaking up the world of AI, Mixture of Experts, or MOE for short. And look, this isn't just some minor update. It's a fundamentally different way to think about building the biggest, most powerful AI models out there.
So get a load of this. It sounds completely backwards, doesn't it? We're building these absolutely massive AI models, packing them with trillions of parameters, only to find out they use less than 10% of their brain power for any single thing you ask them to do. But here's the twist. This isn't a bug, it's a feature. In fact, it's the secret sauce that's unlocking the next level of AI.
You know, for the longest time, the motto in AI was pretty simple. Bigger is always better. If you wanted a smarter model, you just kept stuffing it with more and more parameters. But that whole brute force approach, what we call dense models, has slammed right into a massive wall. The cost and the time it takes to train them has just become, well, insane. To really put that in perspective, just look at this number. 3.3 million. That's how many GPU hours it took to train Meta's Llama 2 model on top-of-the-line NVIDIA hardware. I mean, that's like having one single GPU running non-stop for 376 years. The amount of energy, the cost, it's just staggering. So clearly, just making these things bigger and bigger isn't going to work. We need a smarter way forward.
So what's the solution? Well, it lies in a completely different strategy, Mixture of Experts. The whole idea is to stop trying to build one giant do-it-all brain, and instead to build something more like a super-efficient team of specialists.
Think about it like this. Instead of one person trying to be a world-class coder, a lawyer, a poet, and a physicist all at the same time, which is impossible, you have a different expert for each one of those fields. And this is the crucial part, you have a smart dispatcher who instantly knows which expert to send your question to. That, in a nutshell, is the genius behind MOE. Okay, so here's the more technical definition. An MOE architecture basically swaps out certain parts of a traditional AI model with a bunch of these smaller, specialized expert networks. Then you have a routing system that intelligently picks just one or two of these experts to handle whatever input comes in. That's the magic trick right there. You get all the knowledge of a gigantic model, but with the speed and efficiency of a much, much smaller one. So if you pop the hood on an MOE model, you'll really find two key parts. First, you've got the expert networks. These are your specialists. And in today's models, you might have 8 of them, or you might have thousands. And second, you've got the gating network, which we call the router. This is our smart dispatcher. It's a small network, but its only job is to direct traffic, and it gets incredibly good at it.
And that brings us to the real heart of the whole system, that smart router. This is where all the magic happens. Its ability to intelligently pick and choose only the experts it needs is what makes this whole powerful idea of sparse activation possible.
Let's take a real-world example that honestly trips a lot of people up. Mixtral 8x7b. When you see that name, it kind of sounds like you have 8 separate 7 billion parameter models all working at once, right? Like you're using 56 billion parameters for everything. But that's not at all how it works. This table really lays it all out, the myth versus the reality. On the left, you've got the myth. 8 separate models, 56 billion parameters all firing at once. But the reality, on the right, is so much smarter. Mixtral is one single model that has 8 experts inside it. And for any given token, the router only picks 2 of them. So even though the model has a massive 47 billion total parameters, you're only ever using about 12.9 billion of them at any given moment. And this quote just nails the payoff, doesn't it? You get the knowledge and the power of a nearly 50 billion parameter model, but the actual speed, the cost of running it, is more like a much smaller 12 billion parameter model. It is literally the best of both worlds. And this core idea, this is what we call sparse activation. Sometimes you'll hear it called conditional computation. It's simple, really. Just like you wouldn't get your entire company in a room for every tiny decision, the model only activates the tiny fraction of its brain it actually needs for the job at hand. It's just a radically more efficient way to compute.
So does this specialization thing really happen, or is it just a cool theory? Well, researchers at NVIDIA decided to put it to the test. They started feeding Mixtral a bunch of questions about abstract algebra and just watched what the router did, and the results were crystal clear. It almost always called on 2 specific experts, number 3 and number 8, to do the math.
But here's where it gets really amazing. When they switched the topic from math to professional law, the router's behavior totally changed. It benched the math experts and instead lit up a completely different one, expert number 4. This is the smoking gun. It's definitive proof that these experts are really learning to specialize in their own unique domains.
Okay, so MOE models are faster, they're more efficient, they specialize. It sounds like the perfect solution, right? The end of the story? Well, like with any new technology, there are always trade-offs. There's no such thing as a free lunch. So on one hand, the payoffs are huge. We're talking faster training, way lower compute costs, faster inference. It's a win-win-win. But on the other side, you've got the challenges. And the single biggest catch with MO models today is their massive need for memory, or VRAM. Let's dig into why that is.
I think the best way to understand this VRAM problem is with this analogy. Think of it like a huge office building. Even though you might only need 2 of your experts for a specific meeting, you still have to rent and power the entire building just so the whole team can be on standby. All 47 billion of Mixtral's parameters have to be loaded into your GPU's memory at all times, even when you're only using a tiny slice of them.
But look, even with that VRAM challenge, this whole move towards sparse, MOE models is a huge deal. This isn't just about one cool model. It really feels like a new chapter for how we build artificial intelligence.
The numbers are just hard to argue with. We're seeing that an MOE model can hit the same quality level up to 3 times faster than a traditional dense model. In an industry where computing power is basically the most precious resource, a 3x speedup isn't just a nice little improvement, it's an absolute game changer. It unlocks the ability to train models at a scale we couldn't even dream of before.
So let's just quickly wrap up the big ideas here. First, mixture of experts completely shatters the old rule that a bigger model has to mean more work. It lets us build these AIs with enormous capacity that are still incredibly efficient to run. This idea of conditional computation, of sparsity, is the key that's finally going to let us build and actually use models with trillions of parameters.
And that kind of leaves us with this big, fascinating question to chew on. For so long, we've thought of intelligence as just more data, more power, more computation. But MOE shows us a future where intelligence is actually about efficiency, about specialization. A future where AI achieves more by doing less. And if that's where AI is headed, well, what does that say about our own definition of intelligence?